All right, let's dive in. Today, we're going to unpack one of the most powerful ideas in all of mathematics. And what's so wild is that it all starts with something so simple, you literally use it every single day without even thinking about it.
You know, this quote from the great mathematician G.H. Hardy, it really gets at something huge. He's talking about a concept that's totally timeless, something that's been around forever, but is also constantly new. It's the bedrock, and that's what we're digging into today.
So what is this big, fundamental idea? I mean, really think about it. What could possibly be so simple yet so incredibly powerful that it underpins pretty much everything else in math?
Well, you already know the answer. It's just the idea of a collection, a group of things. That's it. You deal with this stuff constantly. A pack of cards, a cricket team, a crowd, even the vowels in the alphabet. They're all just collections of distinct objects. You've been doing this your whole life.
Okay, so in the math world, we have a special name for these collections. We call them sets. But, and this is a big but, there's one huge rule that separates any old collection from a proper mathematical set. And here it is. A set is a well-defined collection of objects. Those two little words, well-defined, that's the secret sauce. That's what gives this whole simple idea all of its power.
But what does that actually mean, well-defined? How can you tell if a collection makes the cut or not? Turns out it's way simpler than it sounds.
This chart breaks it down perfectly. On the left, you've got things that are crystal clear, totally objective. The vowels are A, E, I, O, and U, period. There's no argument about whether something belongs or not. But on the right, it's all subjective. Who are the most renowned mathematicians? Who decides the best batsman? Since it's all a matter of opinion, we can't call it a mathematical set. It's just not well defined. Okay, so we've got a handle on what a set is. Now, how do mathematicians actually, write them down? Well, there are two standard ways, and they're both super straightforward. The first way is called roster form, and it's exactly what it sounds like. Think of a team roster. You're just listing out every single member of the team, or in this case, the set. You just stick them inside these curly braces, pop some commas in between, and you're done.
The second method sounds a bit more complex, but I promise it's not. It's called set builder form. Instead of listing everything out, which could take forever, you just state the rule for getting into the club. This example here basically reads as the set of all things, let's call them x, such that x is an odd natural number less than 10. It's just a really efficient way to describe a set, especially a huge one.
Now, when you're using that first method, roster form, there are two key things you got to remember. First, order doesn't matter at all. The set 1, 2, 3 is exactly the same as 3, 1, 2. Second, you never repeat elements. For example, the word school has two O's, right? But the set of letters is just S, C, H, O. The O is only listed once.
Awesome. You've got the basics down. So now, let's do a quick-fire tour of a few special types of sets you're going to see all the time.
First up, the empty set. And yep, it's exactly what it sounds like. A set with absolutely nothing in it. A collection of zero things. It gets this cool symbol, the Greek letter phi, or you can just write two empty curly braces. It might seem a little weird, but trust me, this idea is super important. Next, we have this big split. Finite sets versus infinite sets. A finite set is one you could, in theory, finish counting, like the days of the week. An infinite set, well, it goes on forever, like all the odd numbers. And see those three little dots, the ellipsis, on the right? That's your visual clue. That's math speak for and so on, forever.
This all leads to a really important question. When can we look at two sets that might look different and say they're actually the same thing? In math, the definition for this is super precise.
Two sets, let's call them A and B, are equal if and only if they have exactly the same elements. Not a similar number, not similar kinds of elements, but the exact same members. Every single thing in A has to be in B, and every single thing in B has to be in A.
Okay, let's make this super concrete. Take the set of letters in the word alloy. Remembering our rules, no repeats. That gives us A, L, O, Y. Now, what about the letters in loyal? That gives us L, O, Y, A. So are they equal? Yes, absolutely, because order doesn't matter and they have the exact same elements.
So, we've defined sets, we've learned how to write them, we've looked at a few different kinds, but you might be thinking, okay, but why? Why does this simple idea matter so much?
Because sets are the absolute foundation, the building blocks, of pretty much all modern math. You can't even define what a function is without using sets. A function is basically just a rule that connects an element from one set to an element in another. Even probability theory, that's all built on sets of possible outcomes. It's the language everything else is written in.
And the rabbit hole goes deeper. This idea doesn't just stop here. It builds on itself. The next logical step is this idea of subsets, which is just talking about sets that live inside of other sets. Think about it. The set of students in your class is a subset of all the students in your school. It just lets us describe things with even more precision.
So, when you boil it all down, we've seen how this totally normal, everyday idea of just grouping stuff together can become a powerful mathematical language, all thanks to one little rule. It really makes you wonder, right? What other huge, powerful ideas are just hiding in plain sight, waiting for us to notice them?